All right, good afternoon, everyone. I'm John Waddell, and I'm here with Charles Nutter today. He's been working on a new language called Mirah, which I've been working with, and Ryan Brown from Google has also been doing some work with it. And we're real excited to see where it's at today. Take it away, Charles.
Okay. Well, hi. This is my first Tech Talk at Google. It's fun to be here. We'll jump right in. My basic info. Been doing Java for a long time, JRuby for like 5 years now, full time. And now working a little bit on another language called Mirah that we'll kind of get to in the second half of this. So first of all, I want to see like who's doing JVM based stuff, first of all. Okay, so most of the folks. Is it mostly Java? Or, yeah, Java? Any Scala folks? No? Closure? Like playing with it maybe a little bit? Anybody doing any dynamic language work? Okay. Python? Mostly? No? Ruby? Closure? No? What? Other? Okay. Well, that gives me a good sort of picture of where we're at. So the focus of all the stuff I'm going to talk about today is on the JVM. I'm not a VM engineer. I'm fine using the JVM. I'm happy with it. So the efforts that we're putting in on JRuby and now on Mirah are for me someday in the future when I start actually writing real applications to do more work in less time, be able to use the tools I want and the languages I want. And the JVM is obviously an excellent platform, but you know it's not all wine and roses all the time. Java is a little bit cumbersome. I don't find it to be a particularly bad language, but it is a bit verbose and a bit large sometimes. There's a lot of interest in fixing that. Lots of different JVM languages now, more than are really going to be practically applicable probably, but lots of experimentation. And they all, unfortunately, introduce all their own quirks. Dynamic languages have their performance considerations. The statically typed languages are sometimes overcomplicated or have their own runtime library requirements or version-to-version incompatibilities, things like that. So we've got a lot of different tools, and I'm going to look at two today. So first off, I'm going to talk a little bit about where JRuby stands, what we've been doing with it, what other people are doing with it. So compatible with Ruby 1.8.7, we're working on 1.9 support as that sort of solidifies. And it's just Ruby on the JVM, but it's a lot more than just doing Ruby. So I'll do a quick little playing around with demonstration here. So let's see, JRuby demos. All right, so I think I'll just go with the MIDI demo because that's a fun one. Okay, so this will open up a little window and it's just going to listen for, let's pick the right Java. There. This will open up a little window and listen for key events and basically turn the key events directly into MIDI notes and play it. So it's like, you can actually hear that? Actually, the numbers seem like they're in the right key code or ASCII range to be a good scale. All right, so that's a little example. Let's take a look at what the code looks like for that. And of course, this is just using Java swing libraries, Java MIDI libraries. Oh, a little splash of assembly there. That was fun. Okay, so this is all just pretty ordinary Ruby code. And really, other than the preamble stuff that's kind of typical to Java, none of this looks like it's anything but regular Ruby. Open up a MIDI synthesizer, get the first channel, open up a frame to receive events, and then for each of the events, turn the notes on and off. That's really all there is to it. And you can do this with pretty much any Java libraries. It's really nice to be able to script this stuff. We put a lot of work in on making that interface feel like Ruby. And it's pretty much like you just have an entirely new set of libraries, all the libraries you're used to on the JVM available from Ruby code. All right, so that's the basics. It's not too hard to understand this stuff. This is just Ruby on the JVM, and you can do everything that you could do with other languages on the JVM. So I know there's not a whole lot of Ruby going on at Google. What kind of things have you guys heard? And these are the three that I keep hearing from people, that Ruby's slow, right? Ruby can't scale. Obviously, Twitter had to switch away from Ruby, at least for part of things, because it doesn't scale. Deployment sucks. Rails doesn't work well in existing organizations, existing platforms. So I figured I'd go through these and talk a little bit about why they may have been true at one point, but they're certainly not now. So as far as speed goes, it is true that regular Ruby 1.8, the standard day-to-day implementation most people use, is not fast. Of the mainstream languages, if you want to talk like the top 10 or 20 languages that people use, it probably has the distinction of being the slowest out of those. But that's talking about an implementation that's really not changed substantially in 10 years or so. Ruby 1.9, which does include, which is a bytecode-based engine, has a lot of performance improvements, is now, by most measures, about as fast as running Python, which is at least as good. If you're used to using Python, you know you can get the same sort of performance out of Ruby. And JRuby is actually as fast or faster than Ruby 1.9 on most measurements, small applications, benchmarks, whatever. And so how does this actually work? Most of the time when we talk about JRuby, people expect that it's not going to be as fast as the C implementation at the very least. But most people think that it's going to be Ruby running mostly interpreted on top of the JVM. Might be able to get some of the JVM benefits, but it's probably worth looking at 3 different areas that are important for what it means to make Ruby run fast. The biggest one, I think the most important one, is that all the core classes, strings, arrays, hashes, etc., they need to be as fast as possible. You have to have good memory management because Ruby is a very memory-intensive language. And then, eventually, being able to run the Ruby code itself as fast as possible is kind of the last mile for performance. So as far as JRuby goes, all of the core classes, strings and arrays and whatnot, they're all implemented in Java. So we get that performance automatically. They've been refined for several years that we've been working on JRuby, using whatever tricks we can find from the C implementation, tricks that we know on the JVM. And of course, the performance is never perfect for these, but it's trending well. And pretty much any of the core classes in JRuby should be faster than the C implementation's versions. And if they're not, we want to know and we want to fix it. So there's a lot of effort going into that. Memory management, I probably don't need to say a whole lot about this. The vast majority of Ruby applications that we see on the standard implementations eventually bottleneck on GC. The process gets too big, conservative collector can't keep up with it, you're cranking through too many objects, the heap space gets fragmented, and you've got a lot more space to scan. So JRuby, using the JVM, this is almost a non-issue for us. We do crank through a lot of objects. We actually end up hitting allocation rates as a bottleneck more often than GC. The GC is still barely a blip on the performance schedules. But we're doing way better than just about any of the other implementations, just because we're piggybacking on the JVM. So then the final one is actually being able to run Ruby code fast, which is where I spend most of my time on JRuby. So JRuby is mixed mode. We do have an interpreter for Ruby code, which means we can run on phones, things like that. But we do switch over and JIT that code as it gets hot. It's fairly naive right now. After about 50 invocations, we'll compile that method. And then the JVM takes over. If we put everything in the right place, if we line up all the calls, if we're very careful and very nice about how we generate that bytecode, the JVM will run with it and do the additional layers of optimization for us. So can we make this faster? Right now, saying that we're around 1.9 performance is pretty good. We don't spend a whole lot of time worrying about it. And for everybody that's running applications on this, they're able to get stuff to run just about as fast as they need. But we want to go more. There's another level of performance that we could get. And the fact is, since we're actually running mixed mode, since we have an interpreter, we could be doing a lot more as far as optimization. The current compiler, when it compiles the code, is really not doing anything other than static optimizations, looking for specific patterns, trying to reduce the use of heap-based scopes if it doesn't seem like they're going to be used. Very naive, very top-level sort of optimizations, and that's gotten us very far at this point. We've done a good job with that. But since we are running the interpreter, we can gather information like what calls are being made and what values are being used, the types of objects coming in, and start using that a bit more to optimize the eventual compiled code. So it's a work in progress, but some of the stuff that we're working on now, probably some of this will be in JRuby 1.6. We can look and see what the exact target method was. In many cases now, we can actually turn that into a direct static call with none of the normal dynamic call plumbing. We're starting to look at doing actual local variable optimizations like propagating values, propagating types, unboxing when possible, reducing fixed num algorithms, fixed num math down to raw int or long math. So this stuff is all kind of a work in progress. We're looking at the future things, the harder parts that we may eventually need to do. We'd like to be able to be really aggressive as far as optimizations and back off if it turns out that we're wrong. Now, JVM does this all the time, but it's harder for us. We actually do need to do all the de-optimization work manually. So this stuff will probably come a little bit later. And possibly looking at doing manual inlining for at least trivial methods or small methods that don't have a lot of side effects on them. So the dynopt work is what I'm calling this right now for JRuby. What works at the moment is being able to take the last method and do a static dispatch to it. It adds a little guard based on the serial number of the type it saw. So it's kind of a type check and a modification check all in one. There's some implicits for a few of the core types, so it can call directly into fixed nums and floats and whatnot. And there's an optimization for recursive calls. So let's take a look and see what this looks like. Okay. All right. So we'll go back to JRuby. All right, so we'll just use a stupid benchmark like fib, which actually ends up being, in JRuby, more an object allocation benchmark than just about anything else. The call-to-call performance doesn't make a great deal of difference. It doesn't show up in profiles, but because we have to allocate fixed num objects all the time for a normal object passing call path, we crank through lots and lots of objects and the allocation cost actually gets to us. I've actually done some measurements that shows that on a benchmark like this, numeric algorithms, we end up saturating the memory pipeline, just trying to grab all those objects so quickly. So how can we improve that? Let's take a look and see what it runs like normally. Bench fib recursive. I think this is just doing fib 30. So we'll see how that works out. Dash server. Okay, so around 0.2. I think Ruby 1.9 runs this in like 0.3 or so about 30% better or so. There are some implementations that run faster than this. A lot of the Ruby implementations, one way that they're able to do fast on integer math at least is that they use what's called a tagged pointer. The first bit or couple bits of all of their memory references are just basically used as flags to know whether it's actually a fixed num value. So they support 30 bits or 62-bit values, and then they're able to pass them around as though they were references. We don't have that on the JVM, so we pay that allocation cost. But if we can actually start lining up code a little bit better for the JVM, it can start to eliminate some of those allocations. It can actually start to help us a lot more than if we just did straight up dynamic dispatch. Now, the first thing I'll show you, now this will be fun. How many people spend a lot of time looking at JVM bytecode? Just raw JVM bytecode. Well, you're going to look at it now. All right. This is what I do all day long. I look at JVM bytecode and assembly traces from Hotspot. Okay, so let's go find the fib method. There's the file method. Bytecode. Let's see, fib Ruby. Okay, so here's the actual method. And the interesting bit here is up at the top, we do get call site 1, and we load some arguments into it, and eventually do this invocation. Now, this is actually what we do every single time we have a math operation. We're doing an invocation through a dynamic call site to fixnum, and that eventually will do the math, return a value for us. Now, if we turn on some of the dynopt stuff, dynopt equals true. All right, let's crank through this. So let's see what the performance looks like on this. So now what this is doing is it's going to continue. Oh, I piped it. Okay, good enough. So it was about 0.2 before. With the dynamic optimizations, we're getting down below 0.1 for this. And what's happening here is it's not immediately compiling it, not doing the naive compilations, letting it run for a little while. So the first result there you see was a little bit slower than the first result in the previous example. But as it runs, it's able to pick up that, all right, it's calling fixnum plus and fixnum minus. It's calling this fib function recursively. All of this stuff ends up playing into our hands, so to speak. So we can actually, let's take a look at the bytecode for this. No, compile. The other JRuby guys love that I keep adding all these properties. Okay, so I'll actually dump out the bytecode for this now. Okay, so we see a number of different methods. This is the one that actually ends up being fib here, this chunk. Let's make that a little bigger so you can see. Now remember up at the top there where we actually were going and getting the call site. Now what we have is basically this code here. So what's happening here, we're doing all the same loads, getting the variables in the right places, but you see this LDC 499. So it's loading a constant 499, which was the serial number of the fixnum class at the time this compiled, loading that directly into the bytecode, and then it does a check, a guard in front of that says, okay, is this the same type? Has it changed since last time? If not, we go through and we proceed to just cast it to a fixnum and do a direct invocation to the less than method. That's the first one up in that in the fib algorithm. If it fails, then down here it'll do the original slow version of the dynamic invocation. So it's still true to Ruby, but it puts all of the static invocations in there, so the JVM is actually able to inline this stuff a whole lot better and optimize it much more. So that's work that we're doing now. On an algorithm like this, I've run a couple benchmarks, a couple tests, and this essentially gets to be as fast as Java using boxed math, which is pretty good. We're not paying any of the dynamic cost anymore. We're still paying the boxing cost. The next step for this is obviously to say, okay, we're always using fixnums. This variable is always a fixnum. Every single call happens that way. Can we just do a fast version that's doing long math, and then have a slow version that does the dynamic version with objects if we need to? And that is coming up as well. That actually won't be too difficult to do. All right, so that's the performance kind of stuff. Now the scaling thing, there's a lot of different ways to scale applications. Most of them boil down to, at some level, processes are threaded in some way. Maybe lightweight processes and lightweight threads, but essentially you have a lot of these little bits and pieces of execution that are running on. And it's true that the C implementations of Ruby are not concurrent. Like Python, they have a global lock, and even though 1.9 does use actual native threads, they're still all blocking on each other, waiting for stuff to happen. Sometimes you can give it up if you're blocking on I/O or if you're blocking on external calls, but you still end up largely having to do process scaling, which can kind of be painful and kind of suck. So now JRuby has always just done Ruby threads as regular Java threads. So you create a Ruby thread, and you're actually running with a regular native thread on the platform. And the JVM handles a lot of the details for us. I think some of the newer Ruby implementations are starting to add concurrent threads, but it's a big challenge unless you plan for it at the beginning. Luckily, we don't have to deal with that. So now the downside of that is that as far as thread safety goes in regular Ruby, it's probably all thread safe as long as you don't actually do anything concurrent, which isn't really that useful to us. People write these wonderful threaded libraries and wonderful actor frameworks and never test them on JRuby. So that's starting to change. People are actually starting to realize that if they want to test for true concurrency and they want to make sure stuff is running well, that they need to run on JRuby. And we're starting to slowly add alternatives, like adding an atomic class to Ruby that basically does what atomic reference or atomic integer can do. Adding some nicer locking primitives, hooking into languages like Clojure, so you can use the Clojure STM and the Clojure data structures entirely from within Ruby. It's all very easy to do, so all of these other options that are on the JVM are just available to you from Ruby as well. So now kind of the truth about threading, every couple of years it changes which is the right way to do concurrency, but there are a few immutable truths. as far as threading goes. So mutable shared state is obviously bad. You have to do your own management, your own synchronization around it. You can just cut that out and say, okay, that's the worst end. Lots and lots of mutable state shared across a bunch of threads, rough times. Immutable shared state is good. If it's immutable, nobody can be concurrently modifying stuff, then everybody's happy. But I think the most applications are probably going to fall into the middle. One of the problems you run into with entirely immutable shared state is that you're cranking through even more objects than Ruby does. You end up burning those allocation rates and GC time very quickly. So if you can use mutable structures only within certain contexts, only within unshared contexts, and then make sure all the shared stuff is immutable, that seems like it's kind of the best balance, right? So along these lines, in about Rails 2.2 or so, there was a big effort to make Rails itself thread safe. They were sort of coming under attack from other Ruby frameworks that made this decision early on. And they realized that they needed to clean this up. They wanted to be able to run multiple requests through a given process, through a given instance, and not have to worry about the thread safety issues and not have to pay the cost of all those processes all the time. So it actually runs really well now. That has continued on through Rails 2.3 and Rails 2.3 and Rails 3.0, which is now in RC. So if we go from here to concurrency, or to deployment, I can actually show a little bit of this. So deployment has definitely sucked for Rails and Ruby stuff, and it's still kind of goofy. Almost all deployments of regular Ruby applications are still trying to manage end processes. And you look at the history of this, and they're all trying to solve this problem of not being able to use a single process to handle multiple requests at the same time. So it started out basic CGI stuff, fast CGI, so it would pre-spin things for you and manage those things in the background. Then Mongrel came along, and it was a much better server, but you still had to have an external manager killing processes that went bad and starting them up and making sure things were still running. Passenger has done a lot better on this. They do all of the management of those processes for you, and it's considered one of their best features that if a process starts going crazy, that they can just kill it and start another one, which on the surface that seems great, but it would be nice if you actually didn't ever have to kill that process and you just could run and have it keep going and be rock solid, right? So this is the basic plan for scaling Ruby and Rails on regular C Ruby. You got an n-way machine, and then you can just choose the way you want to die. Because you're going to have whatever your formula is, n+1 or 2n+1 instances, processes, to be able to saturate that machine. These applications grow and grow. There's no upper bound on the limits of the regular C implementation as far as memory, and the fragmentation and conservative GC stuff contributes to that as well. So essentially, we got people running with gigs and gigs of Ruby processes in memory just to be able to saturate a machine. And that was like the what WTF moment for me when I came into the Ruby community. I was like, what year is this? So the nice thing about this is since everybody's always scaled with processes, none of these individual Rails instances actually shares anything. The shared nothing architecture is alive and well in Rails, and sessions are usually back in the database or in memcached or pushed to the browser in a cookie. There's very little mutable state that actually exists within Rails itself. And that seems to be trending towards something, right? So thread-safe Rails, really the big things they had to do was go through and all the lazy loading libraries, make sure that they eagerly load them if they know you're going to be in thread-safe mode. Any of the mutable structures that they do have, they did a little bit of wrapping and cleaned those up. Almost all the other shared stuff, they made immutable. And just constructing the whole request pipeline fresh for every single request. So now you really can do with JRuby, for example, one instance, actually one process or one application deployed to a Java app server and handle all the requests you want and actually scale across all the cores. So the concurrency thing is a bit of a myth. Let's actually show what this looks like. All right, so I got a really simple app here. So a little simple Rails app, and I have a little demo controller in here. All right, only two little actions here. And then actually the interesting one here is going to be the slow one, where we're going to simulate some sort of blocking call or some sort of delay in the request processing. So if we actually hit this, localhost, foo slow. All right, so it's going to take, actually start the server up. That would be a good thing to do too. Trinidad. So Trinidad is actually one of the little embedded servers that we have for JRuby. It essentially takes just the web components of Tomcat and puts a nice little Ruby command line on it, and you can run a server just like that. So Trinidad thread safe. We'll run production, so there's no other stuff going on. Okay, test app. I can just do it like this. All right, so we start up our little Trinidad Tomcat Rails server. And should be up and going now. Bootstrap JRuby a little bit. Okay, so there we've got our process. We've got our little controller, and every request is about half a second, right? That's like we'd expect. So let's actually play with this a little bit and see what sort of requests we can crank through it. We'll just do 10 requests to localhost. Slow, okay? So this should take about 5 seconds. It's about right. A little less than 2 requests per second. Now, if this was regular Ruby, if this was the C implementation, you'd pretty much be stuck. You'd have to spin up multiple processes to handle all the load. And then you have to manage however many processes. And as the requests get more complicated and take longer, you're going to be just scaling out with processes all over the place and trying to manage them, watching them grow, watching them die. It's like a little family, really. If we run this, since we're running this with JRuby and we're running with Tomcat, which is going to be able to crank up all these threads, and we're running in thread safe mode, so it's only the one instance, we can do, fun things like actually shove concurrent requests through this. Let's bring that up a little bit so people can see it. Okay, so it's basic concurrency 2. Should take about half as long on my 2-core system. All right, so concurrency 2, get about 4 requests through per second. Let's go up higher. Let's have fun with that. Concurrency 20 and 100 requests per second. Or 100 requests. So now at this point, we're mostly starting to saturate things, but you can see we're still cranking more and more requests through. Tomcat's going to spin up those threads. It's going to park requests that come in if it doesn't have enough room to process them. But they're all going to keep going. So Rails and Ruby can scale just fine if you're using JRuby. That's kind of the key detail. Performance is good. Scaling's good. I mean, it's really nice framework as well, which I'm not qualified to demonstrate as much, but a lot of those myths about Ruby go away if you use the right implementation and the right platform. So that was kind of the point of these first section, okay? Now, of course, you can do all the stuff on the platform that you want to do. You saw I called into MIDI libraries and swing libraries, and that stuff all works fine. All the tools that are available for the JVM, they work great with JRuby. There's really not any reason to use it, or not any reason not to use it, other than, if you're just not a Ruby fan. So there's some new frontiers for us. A couple of these are familiar to you guys. App Engine. There's a lot of folks doing JRuby applications on App Engine. Because JRuby can just bundle up as a web application, actually I'll show you that quick. So let's say we want to turn this into a Java web app. Here in my Rails directory, there's a library you can install called Warbler, and that gives you a warble command. And what this will actually do is it'll pull down the Rails libraries, it'll pull down JRuby libraries, bundle everything up, and in the end we have just a WAR file. So any Rails app that you're developing, you can just bundle up and toss into any Java application server, use all the same libraries, deploy it alongside all the other apps, and it works just fine. So given that, since we have Google App Engine out there, there's a lot of people that have been putting apps up on Google App Engine using JRuby. There's some nice tooling and some nice libraries to make it easy to help you push it out there. Woody or Ryan can definitely show you some of that if you'd like to see it. What I'm going to show, though, I think is kind of cool. There's some work being done to put Android apps, or make Android apps in JRuby as well. Let's actually jump over there and show one of these. All right, so I got my emulator up. So JRuby, whoops, that's not the right one. JRuby on App Engine, I've dubbed Rubato. I thought that was kind of a clever name. So what we actually have here, I'll zoom in a bit so we can see this nicely. This is a little interactive Ruby console that runs on the phone. Now the nice thing here, we can't actually generate JVM bytecode on the phone. Well, we sort of can. There's some tricky ways that you can get it into DEX format. But we have an interpreter too. So we can actually just generate new code and run new code on the phone and play around with it. So if I just start interactively writing stuff here, puts hello. Let's see, use a Java library, Java lang system, get property, java.home. Okay, things like that. Looks like it's a system on the phone. You know, and actually almost all of this interface is also written in Ruby. And we have a few different demo applications. The one that I like the best is actually the one that goes through and implements the Android API demonstration entirely in Ruby. Now, there's a lot of code here, and I would strongly recommend against doing heavy development with this editor. But you can see we're pulling in Android libraries here. Let's escape out of this. We've got our Rubato activity. We don't have all of the demos there. All right, the point is you can actually write Ruby apps, you can generate new code, you can do all the same stuff on the phone that you would do with Java or any of the other JVM languages, and it works just fine. So Ruby apps for Android is largely a solved problem. We're just working on getting tooling and some of the performance things cleaned up. So let's go back to the slides now. Okay. And like I say, anywhere you got a Java server, you can deploy JRuby stuff like any other application. Okay, so now forget everything I said about JRuby. I'm going to switch from Ruby and all the dynamic language love over to Mirah and the beauty of static typing. Okay. So let's go back and look at what my day job is. I write Java code all day long to work on JRuby. I write Ruby for libraries and for little side applications on occasion, but largely I write Java all the time. I do little JVM utilities, usually surrounding JRuby or for JRuby. I do lots of bytecode generation. It's amazing when you're able to write like 50 lines of bytecode generation and it just runs the first time. That's kind of a scary moment. I've got interest in doing mobile and embedded applications. I've done some really small, like sub-ME embedded Java stuff, where like I had to write my own streams and stuff. Fun, but you know I've got a fairly narrow scope, and within this narrow scope, Ruby has a little bit of trouble fitting. So my problem is that I really do like Ruby. I like the syntax, I like the feel of the language, but I write Java all day long for JRuby. Is there a way that I could start using more Ruby? I mean, we can get Ruby to run really well, but it's going to be hard for it ever to replace, on a performance level, on a footprint level, what we actually do with Java. So the idea for Mirah started like this. What if instead of writing this Java class with all the extra noise that comes along with it, what if instead of writing this, I could actually just write this and lose nothing at all? This is the Ruby class version of this, okay? And that is essentially what we're doing with Mirah. So in Mirah, we're pulling features from various languages. We're pulling syntax from Ruby, the bits and pieces that we like. We're doing local type inference like Scala, and actually some field inference here. And the goal of this, let's take a look. Mirah is kind of, at the moment, like a nicer way to write Java. It's Ruby syntax with a few modifications, like type annotations for parameters coming in. But it ends up feeling a lot like Ruby. and compiles directly down to Java or to JVM bytecode. And you can produce Java source with it as well. That's one thing we've been doing, is keeping feature lockstep so you can generate both Java bytecode and Java source for the equivalent thing. But the key feature here, and I think this is one that has escaped almost all other JVM language implementers, is that we're really working hard to introduce no runtime library at all. The code you write compiles to class files, and that's it. You're done with it, which makes deployment on small devices, deployment on mobile devices, obviously much, much easier. So let's dig in a little bit on this. So features from Ruby that we do have working. Optional arguments. I can show an example of what that looks like. Basic internal iteration. Closures are functional now. Most of the literal types from Ruby. String interpolation is nice to have. We have plans for things like mix-ins and open classes. Those will be coming along. There's other features that we want to pull from, your favorite language of the week. For example, extension methods, doing it something like C# does, but making it look like you're actually opening classes in Ruby, right? Implicit type conversions, possibly from Scala, which opens up a lot of dynamic DSL sort of stuff without actually changing any of the static typing behind the scenes. Pattern matching in case classes. I mean, there's all sorts of stuff that we could do. And I think we can do almost all of these with just a compiler and not introducing any new libraries. That's the goal. That's the goal right now. So let's see what this looks like in practice. Here's a simple the hello world from Ruby and the hello world from Mirah. Identical code, except that this Ruby version is going to require you to immediately ship a 5 or 10 megabyte JRuby jar file along with the application. Hello world has now encumbered you with that library. In this case, there's no other dependencies. So this is the basic code that we end up generating, the bytecode we generate for the Ruby stuff. And in here you probably can see that there's the call site logic, there's some preamble logic, and this isn't even the whole story. The call site logic is going to pick up the puts method from somewhere, it's going to construct the string from somewhere else, and then it's going to do that call dynamically. If you do this with Mirah, we're essentially just turning it into system out print line. Same code, but compiles straight down to regular bytecode and does what you really want it to do under the covers. And then the Java code that we generate. So we have Mirah just spitting out regular Java code that does basically what you would write if you're going to write it in Java. Another example, we go back to fib. There's the Ruby code. There's the only change required for Mirah. Now, of course, there's no way you can read this. There's about 6 different call sites in there. It's constructing all the fixed num objects, doing all of the dynamic calls in there. We'll be able to improve this with some of the dynamic optimization stuff in JRuby, but it's still a lot of noise and a lot of overhead. The bytecode for Mirah. Essentially, it's almost identical to what you would have if you wrote the code in Java and compiled it with Java-C. And then the Java code, of course, which is not the most beautiful thing yet, but we can always pretty print that or something. Optional arguments. Now, of course, in this case, we probably could infer that both of these are ints and just go with that. At the moment, the way that the optional argument syntax works, we do have the type on there as well. And here's just the Java code for that. Chaining the methods just the same way that you would if you wanted to create a series of overloads with optional arguments. The Ruby code for simple internal iteration. Mirah code is essentially identical. And there's the Java code it generates. And you'll see we're doing the same thing as Java 7 at this point, creating an unmodifiable list of those values, and then doing like a Java 5 for loop, pulling the iterator out and doing all the iteration for you. But it looks and feels like you're actually doing a regular Ruby iteration. So things like each and map and select and whatnot, they're all available just by using the existing patterns of what works on the JVM without extra libraries. A simple closure. So here I'm actually creating a new thread with the closure, and the logic there is just to print out some text. Again, same thing in Mirah. And here's the Java code we generate for it. So digging into this a little bit, we're creating a little binding class that's going to hold the mutable closed over state, and then creating a little runnable class, both as little inner classes all behind the scenes. So closures in this case end up just being sugar over doing anonymous inner classes. Anywhere you've got a single method interface, you can just have a closure, a block of code. And it infers the types of the arguments, infers all that stuff, looks like Ruby and feels like Ruby, but it's actually just doing all the noise of an inner class that you would normally have to do. Okay, so now it's important to point out that this isn't Ruby. This is just using Java's library. It's basically Java's type system. You don't have things like eval and mutable classes. We can make it seem like you're opening classes up, but it's not Ruby. It's a lot of the things I really liked about Ruby, the apparent features of the language, on top of Java. So I can use those features, and nobody really even needs to know I'm running Ruby. And actually, you could have like a commit hook that generates the Java code if you really want. But that's the thing, it feels like Ruby. All of these features that people talk about that they like so much about Ruby, in 90% of the cases, they're surface level features. They're skin deep, just syntactic sugar, syntactic niceness. And you hear a lot about new languages that say, well, our syntax is just as nice as Ruby. And it just seemed logical to me, why don't we start with Ruby syntax and see how far we can go to compile it down to the fastest possible bytecode, no runtime library. We'll see how far we can take it. All right, so now a little more fun with Mirah, just to show a little bit more interesting code for this. There's an application for Android called Garrett, written by Phil Hagelberg. It's kind of a playing around with Mirah. So let's open that code up and see what it looks like. All right. So we've got all this application noise around it and one file here. Let's make this a little bigger. All right, so we'll walk through this a little bit. Now, obviously it looks a lot like Ruby, right? Because it's just using Ruby syntax and Ruby parser. We've got a few imports. And from here on down, the only things that are really going to be different from if you were to write this actually in Ruby code are anywhere we have to clarify or narrow it or cast a type. So here we're declaring the variable A is a context. Here we're making sure that these are stored as floats in what essentially gets inferred as fields on this class, x and y and radius. And the rest of this is all pretty much just Ruby. We've got the bounce logic. You're starting to get curious about what this does, aren't you? Move. We've got the touch events we're doing stuff with. Release, what does that do? Historical X. Oh, so we're tracking some stuff, tracking some deltas. And then drawing circles, drawing some text on it. Let's actually see what this application looks like. Now it's actually interesting to note this, again, this is all the code. You compile this and you get a couple class files out of it. No additional dependencies, no external dependencies other than all the Android stuff you're using, right? And it looks nice. If you like Ruby syntax, this is pretty clean stuff. All right, let's go find this app. Garrett. I have no idea where you got that icon from. Okay. There we go. So let's play our little game. Actually, this used to be just a bouncing ball, but I thought I'd turn it into an interesting game. So we're going to grab this ball and just throw it as hard as we can. Okay. There it goes. What's my score? Still going. 31, 32. I don't think it's going to make it. 33, it looks like. I think this version I've still got it limited to a velocity of 50 max. But, oh, it did make it. Sweet, 34. Okay. So let's go back to the code in the app. And like this is all Ruby. But when you compile it down, let's see how big these applications are. If you were going to make an application like this with JRuby, for example, and ship it, you'd need to strip a bunch of stuff out. The JRuby jar is anywhere from 5 to 8 meg, depending on how it's compressed. The DEX process can strip it down a bit more, but you're still going to have to ship a pretty big application. I think that Rubato IRB app clocks in at about 10 meg. And it's in the marketplace, so you can install it if you like. But it's a big app. It's a lot of stuff to ship. This So I've got debug builds here, 16K. You know? And it's essentially the same code you would write if you're going to write this in Ruby. But compiling it straight down, we don't have to worry about all the extra dependencies on a Ruby runtime. Hey, Woody, where would I go? Let's see. Let's take a look at Dubious. That would be good. And that's on the Mirah account, right? Let's take a look at this one. I'll just look at the code here. So on the web side, Dubious is a little framework that's written pretty much all in Mirah, but doesn't have the dependencies on a runtime library, other than a few little things that it ships with. Doesn't have a language runtime that it requires, and it runs really fast because it compiles everything to Java code. So let's make this bigger so you can see. All right, so here we go. Again, like we did with Mirah, we like Ruby syntax, we like the way it feels. Let's start from there. Woody decided he likes the way Rails applications are laid out, the way they're structured. Let's start with that and see if we can actually do the entire application in Mirah instead of doing Rails. Let's take a look at a controller here. Contacts is the good one here. Contacts controller.
It might be easier to browse the actual app.
You have the generated Java code in there too, right? All right. So what was it? Dubious demo.spot.com. All right, here we go. He even sort of copied the Rails front page. Isn't that adorable? Okay, so here's our app structure. And now in here, we can take a look at our context controller. Even got syntax highlighting. And largely, again, it looks like Ruby. It looks like you're writing a Rails application. Index, show, new, etc. We got some of these things. What are these curious things down at the bottom? Looks like they're pulling out some templates of some kind, right? And what do those do? Let's go back and take a look. Now, like I say, this all can compile straight down to Java source if you like. You can go to JVM bytecode, but you can also compile it to Java source. If you take context controller and turn it into Java source, this is what you get out. So we've got our index logic. It's actually pulling out a data model here. If we go down and see the different ERBs that were pulled in, the different templates, it's done all of the inclusion of that into this controller, done all the extra logic of turning it into string appends, string buffer appends, string builder appends. And this is essentially all you really need out of this application. But this is the only dependencies you have, other than the Google App Engine stuff that it's running with. You've taken what looks exactly like a Rails app and feels almost as nice as building a Rails app and compiled it straight down to Java source or JVM bytecode. That's the goal with Mirah. All right. So a little bit about the code base and how it works. We're using JRuby's parser right now. Probably going to be reworking that so we have a little bit more flexibility to add minor syntax changes. Like I said, there's a JVM bytecode and a Java source backend. There's also been prototype, proof of concept work to do a C# source code backend. Again, since it doesn't have any specific dependency on the platform or on the type system, you could use the same syntax with different libraries, slightly different inference engine, and output code for other platforms. That's another goal that may come along in the future. Essentially, it does AST transformation, takes the Ruby AST, turns it into our parser neutral Duby AST in the middle, or Mirah AST in the middle, runs type inference over that depending on what the platform is that we're running on, and then generates the code. And at this point, for everything that you've seen here, we've got a Mirah code base with the JVM bytecode and Java source backends that's essentially 10,000 lines of Ruby code. Type inference is all written in Ruby. The code that drives the code generation, not the ASM library itself, but the code that drives that generation is written in Ruby. The AST is Ruby. So here's the basic sequence. Ruby with type annotations and our modified parser comes out and we get a Ruby AST with type nodes. That goes through our transformer to the Duby AST, and we have various plugins along the way and macros that can do sort of compile time, transform time modifications to the code. We run it through the type inference logic, which again can have platform-specific plugins or crazy wild type systems if you like. And we get our typed AST out of that. And then we generate whatever the native code is for the backend. Since we have all the type information, we have the whole structure, we can generate just straight up statically typed JVM bytecode or Java source. So it's small, but there's a lot that you can do with this. And being small means it's very easy to add new features. The optional argument stuff I showed you, I think, was 50 lines of Ruby code to add that. It takes almost nothing to add additional features to the language. How much code did adding literal hashes cost, do you think? Not much. I mean, I think I added literal arrays that do the unmodifiable array list in like 30 lines of Ruby code. So you can kind of build the language the way you want. Build the language around your application or around the libraries you're running with. So places where this is being used today, the Java bits and pieces in the JRuby app engine tooling is actually written in Mirah. I showed you Dubious. There's a contributor on the list that's actually adding the bits and pieces necessary to do GWT applications, writing in Mirah instead. I think the main thing was just getting the little inline JavaScript native things to work. Of course, I showed some early Android experiments, and it's a young code base, but there's a lot of fun stuff you can do with it, and there's a lot of hacking going on right now. All right, so I showed you the apps. Okay, so futures for this. The code base has kind of grown organically. It's still only 10,000 lines of code, but we want to clean it up a little bit and isolate the different tiers better. I mentioned the parser. I want to actually formalize and expand the type system and actually learn how to make a type system. Get the remaining features from Java, like Java 1. We're at like Java 1.0 level. There's a few little things that are above that. But figuring out whether or not we're going to do generics, enums, other Java 5 features, and additional backends and maybe even front ends. Since we have that standard AST in the middle, there's no reason we couldn't transform other syntaxes. I like the Ruby syntax. Some people are married to curly braces and they really need curly brace syntax. But there's lots of possibilities for this. Just building up a nice tool chain that can generate all this stuff for you. All right, so then the final plugs that I'll do, and we'll have some questions. We do have a Using JRuby book that's in beta now. So if you want to get the basic overview of a lot of different areas of JRuby, you can pick that up. We had a JRuby conf for the first time last year attached to RubyConf. That was pretty exciting. This year we have 2 conferences planned already. There's JRuby Kaigi attached to Ruby Kaigi in Japan next month. And we have JRubyConf 2010 edition, which is basically taking over the Enterprise Ruby conference that takes place in Columbus. And I think we may have another one next spring, another JRubyConf in Minneapolis, where I'm from. That'll be fun too. Okay, so there's a few links, and that's about all I have. I can open up for questions on Ruby or JRuby or the state of the Ruby world or anything.
Where are you going to start to formalize? How are you going to get the process to formalize the type system?
Well, I think we're probably going to start. So the question was, how are we going to do the process of formalizing the type system? I think we'll probably start by making sure we have everything in there needed to represent at least Java 1.0 level type system. Figure out which of the features that we're doing, like some of the crazier stuff like macros and implicits and whatnot, will fit into that type system nicely. And I guess kind of just looking for suggestions on what features people are interested in from other languages, especially type system oriented ones. We don't want to go completely off the cliff and make a giant nightmarish type system that we can't manage, but we think we can add almost all of the apparent features from those different languages just by minor changes to the type system and compiler. And we're looking for folks that are interested in helping on that stuff too. Yeah, over here.
What's the advantage of having a JVM bytecode compiler versus producing the Java source and using Java C?
That's a good question. The JVM bytecode backend, the question for anybody else is, what's the advantage of having both a JVM bytecode and a Java source backend? Well, initially, since all I do all day is generate JVM bytecode, I just worked on the JVM bytecode backend. Ryan came along, Ryan Brown, who's another Google guy here, and he was interested, at least initially, I think, possibly using Mirah to do GWT stuff. So the Java source was a requirement. At this point, maybe there's not a whole lot of reason to maintain the two backends, but it is nice to have something that's going to do the full bytecode compilation and generation for you, rather than spitting out Java source and then having a second cycle to do the Java C compilation. If you needed to do something along the lines of having circular dependencies or having external Java dependencies that require the full build process to run together, the Java source version is also kind of a nice cheat for that. I think we've talked about only having one backend, but it really isn't a whole lot of effort to maintain both of them. And it actually kind of keeps us honest about where we implement the features of the language. If we can implement all of the features in such a way that they're mostly macros and AST transformations, then having two backends is easy. If we ever start to slip into one backend or the other, we know that we're tying ourselves a little bit too much to one particular format, and doing a C# backend or other backends would be more difficult at that point. So it's kind of an interesting exercise, but may actually have some benefits for the language itself. Other questions? Time is in.
We do have some more time. I could, if you guys want to see, I could dig into the App Engine app a little bit and show you how it actually works. Would you guys like to see that? Okay, and actually, if you don't mind, just bring back that browser you had.
Yeah, sure.
So this app is entirely written in Mirah. There is no Ruby in it whatsoever. The advantage to doing this is that the app spins up in about a second. Java App Engine now supports app.yaml. In order to configure the app, I just modify this app.yaml file. So the app itself has this little properties window that I can see what's going on. The controller that we were looking at is actually this. I'm just basically copying a scaffold generation. I don't need to fill this whole thing out. You can generate an app that looks just like your scaffold, and in this case, I've decided to use unobtrusive JavaScript. And so that's how that works. Now, Charlie showed the app earlier, how we had a controller. The views associated with that are here. I have an edit form. And in this case, I basically looked at what would the Rails scaffold generated file look like and just try it. Just start with whatever Rails is using and then make changes in order to make it work. If I go back to the framework file itself, I have this params object. Down at the bottom here, I have this delete method. Sometimes you want to pass in an ID because you don't have it in the URL. I can generate this Java-style overloaded method chain. We wanted to create something that looked a little bit like data mapper, so my model really is just this. I have a property keyword, I specify the names of the attributes, and I specify which types they are. And you'll see here I'm using App Engine types like postal address and phone number. I also need to have those things imported, so that's what those two import statements do. Now, when I compile that, Ryan Brown's done some great work to create everything I need to access. So instead of going through data nucleus, he's just creating the methods I need based on the attributes that I defined, or the properties I defined. So if you scroll down here and notice he's got some methods where he's handling how to get a hash map of properties, or possibly set the properties, and he's generated all of this code for me. So now I don't worry about type safety. I just do something that feels like I would do with data mapper or active record, I suppose, and it's handled. All right. Well, thank you very much, everybody. Thank you, Charles Nutter.
Thanks.